Okay, so now we're going to be talking about how we actually determine these macro constants, which we can then determine our micro constants from, or we can determine our volumes and everything else we need to know. Well, how we do that normally is we just plot our, if we just have one compartment, we plot our natural log concentration versus time. We get our slope here, which gives us our K, and we determine our y-intercept, which is of course not the natural log of the concentration, but the concentration itself. So we have to take the anti-log of that number to give us our C0, so that our macro constants are C0 e to the negative KT, right? Well, when we have two compartments, as I said, we'll plot our, I'm going to just erase all of this. We plot our natural log, our log concentration time curve, and when we plot it, it looks like this. So it is not straight, so we know we have more than one compartment. So what we have to do then is strip the curve. Now usually I have students learn how to strip the curve, but since we're teaching this way, I just don't think it's worth the hassle. So, but I do want you to understand how you would do it. So what you do is, this is called stripping or feathering a curve. I like stripping because it makes it seem a little more exciting, to be stripping. So we're going to strip the curve, and what you do is you start at the very end of the curve and you figure out where the straight line goes from the end. And in this case, we should do it in red because that's what the picture does. So this is the final phase, as I have here. You find that final straight line, and that will be the slope of this line is the slope of your final phase, or your zeta phase, or we know we only have two compartments here, so it's your K2 here. So the slope is negative K2. Okay, so that's how we find our slope. And then our y-intercept is just going to be right here, right where it crosses the y, or where it crosses the y-axis, right? So our y-intercept, and knowing that we have two compartments ahead of time helps. So it's going to be our slope is K2 and our y-intercept is K2. So here's where we have our slope and our intercept, describing this second compartment, the final slower compartment. Now we still have more of this line we have to describe, right? Because sure, we've got this whole part, but then we've got to figure out we've got to figure out what to do with this whole section that we haven't described yet, right? So the way we do that is that we actually subtract the final phase line from the actual line. So we find out what all these points are along the line. Up here too, I'm not doing a very good job, but all these little points. And we subtract the difference between what the actual line is and what this remaining line is, and we plot those differences here. That's what these green points are, is what we call the remainder, or the difference. So here's the remainder, and we hope and pray that when we get the remainder, that is a straight line, and it does look like a straight line. So that straight line, the slope of that line is the slope of our first compartment, and the y-intercept is the y-intercept of our first compartment. So we subtract that final phase from what's left, and we get what we call the remainder, or the residual, which gives us, as I said, our intercept will be the C1 and the slope will be the K1. Okay, so that is stripping a curve. I'm not going to expect you to be able to strip a curve, but I want you to understand that the resulting log concentration line of a two-compartment model, which is curved, is really just the sum of the first compartment and the second compartment lines. If you add those two together, you'll get the actual line of our drug. So let's just make our concentration of our actual drug, which I'm going to do in blue. So your concentration any time t is going to be equal to your first compartment, e to the negative k1. So these respond to your y-intercept and your slope of that line times t plus the y-intercept of your second compartment, which is here, times k2, your slope of your second compartment, t. Okay? So with your, by stripping the curve, you're going to get your macro constants, which are your y-intercepts. Sometimes they're called A, B, C. In kinetics, everyone does their own thing, which makes it even more difficult, but no one seems to be able to get along and decide. Your macro constants are your y-intercepts and your slopes, and these are model dependent because you have to decide how many compartments you have before you can figure out how many y-intercepts you have and how many slopes you have. Sometimes the slopes are called alpha, beta, gamma, etc. But these are called macro constants. Micro constants are all about the movement from one compartment to the second compartment. So K1, 2 and K2, 1. Just think about where you're starting and where you end up. Where you're starting and where you end up. So this is K1, 2 going this way, K2, 1 going this way, and K1 to out of the body 0 goes there. Okay? Now you can figure out all of your micro constants by using your macro constants. So you start out by figuring K21 first. That might not make sense, but that's how we do it. So you take your y-intercept from your first compartment times your K2 plus your C2 times your K1 all over the sum of the two y-intercepts, and that'll give you your K21. You figure that one out first because you need that to figure out your K10. Your K10 is equal to your slope, these two macro constants, your slopes of your two compartments, and your divided by your micro constant there. And then finally you figure out K12 last because you need both of these micro constants along with these two macro constants to calculate it. So you can calculate all of your micro constants once you get your macro constants. You also can determine your area under the curve this way without using the trapezoidal rule, which should make you all happy. So you can figure out your area under the curve by using your macro constants, your first compartment y-intercept over the slope plus in all your different compartments. They'll give you your area under the curve. You can also figure out clearance by using your dose over the area under the curve once you figure that out here. So you can figure out tons of stuff once you know these macro constants. And that's what we're going to be doing in the workshop. Isn't that exciting? All right, why do we care? Well, we need to be able to identify how many compartments we have if we want to be able to determine how the drug moves around. And the biggest thing is so that we don't assume that the drug is only going into a small compartment instead of a large compartment. If it's starting out here and eventually going out here, we don't want to dose on this, right? Is really kind of the loading dose issue. And we many times really need to understand where we are on this curve, and that it is not a straight line like a one compartment model, in order to be able to make predictions of what actually is going to happen. So understanding multi-compartmental models gives us also a lot of power to understand how the drug is moving around in the body. You can figure out microconstants, you can figure out area of the curves and clearances, and therefore half-lives and all kinds of stuff. Time to steady state, if we know these things. So that's it. Thank you.